Okay. Saraswata, am I audible?
Yes.
So we'll start now.
All
Uh,
right.
Welcome everyone to the second math club talk of this semester. Today's speaker is Saraswata Sensarma from M.Math second year. He is interested in probability, particularly random matrices uh, and related areas. And today he will talk about the semicircular law and its various applications. So what do you, Saraswata?
Thank you so much. Uh, my screen is still visible, right?
Yes, yes, yes.
Okay. So let's start. And by the way, if at any point anybody has any questions, write it in the chat or let me know directly. All right. So let's start. I'll begin with semicircular law comes up in many contexts. It historically came up first in the context of random matrix theory, and today we'll be discussing it only in the context of random matrix theory. So before starting, uh, let's look at the history of random matrices and how this all came to be. One of the first works on this was done by Wishart in the 1930s, where he studied random covariance matrices. By the way, I'll check one more thing. My cursor, etc., is also visible. I hope. Okay. So it began in the 1930s by the work of Wishart, mostly like some in some way, shape, or form. Probably the ideas of random matrices existed because well, randomness existed. The idea of randomness was there, and matrices come up everywhere. So probably people had an idea of random matrices, but formally one of the first works was by Wishart, who studied random covariance matrices, where the matrices had this form. So you maybe sample xi's as IID, like each entry as IID, and then look at such matrices. Such matrices are called Wishart matrices, although this is not always the case. And later on, random matrices were extensively studied by Wigner in the 1950s. Wigner was a physicist and he studied random matrices, particularly random hermitian matrices, because he wanted to approximate the Hamiltonian operators. Basically, so when you have in quantum mechanics, you have this nice Hamiltonian operator, right? This is your Schrodinger equation, hi equals E psi, where h is the Hamiltonian operator and E are the eigenvalues of the Hamiltonian operator. So the eigenvalues correspond to energy levels of the quantum system that you are thinking about. For example, you might look at the Hamiltonian for an atom, hydrogen atom or any atom, and these energy levels would be the corresponding energy of the electron shells. Knowing these energy levels were very, very important for physicists, and that's why they came up with ways of estimating this Hamiltonian operator and knowing the eigenvalues. And for that, uh, Wigner used a class of matrices which are called Wigner matrices. Later on, when people went back and traced the history more carefully, they realized that many of the salient features of random matrix theory, the ideas, the core ideas of random matrices, were present in a paper by Hurwitz back in 1897. He had a paper on Lie groups and Lie algebras where he was talking about measures on those objects. And that paper had many of the core ideas of random matrix theory, but that is more of a like a posteriori conclusion. Okay, so let's talk about the first random matrix model, and this will be our main random matrix model for today's talk, called Wigner matrices. Okay, so we sample random variables. Let's say we have two distributions, uh, xi and xi d. Xi d represents the diagonal. So, and we sample this sort of array of like 2D array of random variables, where each off diagonal entry comes from like off diagonal entries, all of them come from this distribution xi, and the diagonal entries can have some other distribution xi d. Okay, and Wigner gave these sort of assumptions that the expectation of the xi variables is 0 and the variance is 1. So all of these entries have variance 1. The diagonal could be a special case. Okay, the diagonal could be anything, but it doesn't really matter as long as the variance is finite. So off diagonal terms are also IID. Diagonal terms are also IID. And since Wigner was studying Hamiltonian operators are by definition Hermitian. Okay, because eigenvalue, which is the energy, has to be a real number. So the assumptions he made were that xi is a real. If there are two cases, if xi is real valued, then we sample the upper diagonal and make them equal to this lower diagonal thing. Okay, so xij equals xji. This was a condition which was laid out by Wigner. On the other hand, if we want to take xi to be a complex valued random variable, we can just take the conjugate xij equals xji bar for the lower diagonal. Okay, so the model is you sample the upper diagonal and you make the lower diagonal either equal or conjugate depending upon whether you're taking real or complex entries, and the diagonal is always taken to be real so that the matrix remains Hermitian. And we have this array. From this array, the first 1 cross 1 minor, that will be called M1, the second will be called M2, third will be called MT, and this sequence that we get, this sequence will be called the Wigner random matrices or Wigner ensemble, whatever. Okay, and this is what Wigner used to sort of approximate this Hamiltonian operator. He made no claims to what this particular distribution xi might be. Xi can be taken to be a very nice distribution like the normal or the complex normal, these things. But as it turns out, the same results go through in general. They are true for all distributions satisfying these properties. Okay, they're like these sorts of Wigner matrices have a lot of universality, which will be apparent soon. Okay, I hope the model is clear. And what are we interested in? Well, Wigner used them to study, he wanted to know the energy levels. In particular, he wanted to know the eigenvalues of this operator. So mostly in random matrix theory, we're interested in these sorts of spectral properties, right? We are, this class of random matrices are called ensembles. And we are interested mainly in the spectral properties like eigenvalues, singular values, eigenvectors, etc. For today's purposes, we'll mostly be focusing on eigenvalues. Okay. But before we get into the actual meat of the material, I would like to introduce some measure theory. Many of you know this, but I'll just introduce the notations so that we are on the same page. Okay. So, well, all of you know the definition of a probability measure. It's just a set function taking values in 0, 1. Let me use a different color. Yeah, it's a set function taking values in 0, 1, such that the measure of the whole spaces, and for our purposes, we'll only be dealing with probability measures on R. So the measure of the whole space is 1, and it is countably additive. Okay, and this will be our set of measurable sets. We cannot do this for all sets, but we can restrict it to some measurable sets like Borel sets or whatever. But a measure is just a way to give talk about length of the line. Okay, so that the total length of the real line is 1. Okay, so some examples, of course. The first most obvious example is that of the Dirac point mass. So this just assigns value 1 if so delta lambda of A will be a 1 if lambda belongs to this set A, 0 otherwise. And of course, when you have probability measures, you can take convex combinations of those to still get another probability measure. For example, the second one will be a sum of Dirac measures, like a convex combination of Dirac measures, which gives another measure. All right, so this is basically a rescaled counting measure. You can give different kind of weights. For example, let's say you take any PMF, right? PMF, just a second. You take any PMF, all right? PI. Basically, let's start with a random variable which takes values xi with probability pi. Okay. Then you define the measure corresponding to that random variable as mu of a equal to this summation of the probabilities pi's where xi is in a. Basically, this mu a would be the probability that that corresponding random variable is in a. And this is the general construction really. So if you start with a CDF, again, this defines a probability measure. This is also like corresponding to the CDF row. You can integrate it out, integrate over the set A, and that would give you a measure. It's easy to check that both of these conditions hold. So it's a measure. And this is also probability that X is in A, where X is a continuous random variable with the distribution rho. Okay. In fact, what I said, these two previous examples, that is an exact correspondence. Like random variables, real valued random variables, I should say, and probability measures on R are in one-to-one correspondence. You can start from a random variable and get a probability measure by simply looking at this sort of a function. Or conversely, you can start from a measure on the random on the real numbers and come back by looking at a random variable. You can construct a CDF which looks like this. It's just a measure from minus infinity to x, and corresponding to that CDF, you would get a random variable. It's easy to check that this is a CDF. You need some properties of measures, but basically, measures on like probability measures on R and random variables are one and the same thing. They're just two representations of the same thing. Okay. So yeah, we will honor this correspondence by saying that x is distributed as mu. So maybe let me write it down. X is distributed as mu. All of these are like somewhat loose statements. When x is a continuous random variable, we might say x is distributed as a PDF and so on. That we do such bad notations in mathematics, so that's nothing new to you. Okay. Now the question is, why did measures come about? The reason for like development of measure theory was to extend our theory of integration. So whenever one talks about measures, one must talk about how to integrate with respect to measures. And here we are in luck because we are dealing with probability measures on R, right? So whenever you have a probability measure mu on R, there is a corresponding random variable x, as we uh, saw in the last few lines. So the integral, so let's say f is any continuous function. The integral of f with respect to this measure is by definition the expectation of fx, where x follows this measure mu. Okay, x is distributed as mu. Indeed, you can reduce this continuous to like you can include more things. Say piecewise continuous also works. Really, what works are measurable functions, but I don't want to talk about measurable functions. So piecewise continuous will suffice for our purposes. Okay, you just integrate over each piece, and that would be fine. In particular, if this mu is like uniform distribution on 0, 1, you just get the Lebesgue integration or the Riemann integration. Both are the same in this case. Okay. So we had 4 examples of measures, but really 3 examples because 2 and 3 were one and the same thing. We just, here they were equal weights and here they are different weights. Just a second. Before going on, let's explore this correspondence one more time. In the first case, can you tell me the random variable corresponding to this measure? Like this is a probability measure. What can be the random variable corresponding to this? By the way, one thing I might note is that I don't have material for 1.5 hours. So I'll like to keep this interactive and I would like it if you participate. Okay. So can anybody say this?
Uniform on the set A.
Not exactly. This set A is irrelevant. So if I say that probability, so this delta lambda of A is probability that x is in A. We want such an x, right? So probability that x is in A is 1 if lambda belongs to A and 0 otherwise. So the only thing that can happen is x is lambda almost value, right? Corresponding to just delta lambda, we will have this measure. Similarly, if you look at these convex, the summation of delta lambda of A. This just means X can be lambda 1, lambda 1, lambda 2, all the way to lambda n, each with probability 1 over n. Okay, that is precisely this representation. So if I give any set, and yeah, you can verify this for yourself that this will be the case. In the third case, as discussed, this would be like X equal to xi with probability pi. This is sort of a generalization of the previous thing. And finally, in the last case, this is simply X follows. So, I mean, X is a continuous random variable and has a PDF row. Okay. So now let's look at the integration with respect to these measures. Um, for example, if you have a Dirac measure, integral f with respect to d lambda, that is by definition integral of expectation of fx, right? But what was x? The x corresponding to the Dirac measure, the random variable corresponding to it, is lambda almost surely. So the only thing that you get is just f of lambda. So integral with respect to a Dirac measure just is like an evaluation at one point. Let's take another example. If you have summations of these Dirac measures, what do you get? Well, this is just expectation of fx, where x takes values lambda I with probability 1 over n. So this is exactly 1 over n summation f of lambda I. Correct? This is the simple formula for expectation. Similarly, in the third case, when you're taking x equal to, okay, it was xi, but who cares? Okay, here it was written lambda I. So x equal to lambda I with probability pi. So this just becomes summation pi f of lambda I. And in the fourth case, now this is a continuous random variable. X becomes a continuous random variable PDF row. So expectation of fx. So this integral would just be expectation of fx, which is integral fx rho x dx. Now, by the way, you might think that is such a integral sort of well defined. The answer is yes. If you have two random variables with the same distribution, you can the integrations will be the same. Okay. So are there any questions up to this point? Should I repeat something? Should I, because this will be sort of our language for the remainder of the talk. So if you are not comfortable with measures, please let me know now. Okay. And on the concept of measures, there's one last topic. Whenever we have, say, a collection of objects, one natural thing to do is talk about sequences and convergence of those objects. This collection of measures, it's a convex set, right? Any convex combination of measures is another measure, like probability measure. So it's a good idea to talk about convergence here. And well, how can you think about convergence? You can say that, okay, so let's say you have a sequence mu n and you have a measure mu. You can say for every set A, mu n of A should converge to mu of A, right? And that is precisely like for only for measurable sets, otherwise this makes no sense. But this is precisely the idea of weak convergence of measures. And an alternate form of writing this is simply saying that all of these integrals converge. Okay. So I mean, this is sort of like you probably have seen this equivalence that a sequence of random variables converges in distribution if and only if expectation of fxn converges to expectation fx for all f in some set in, let's say, continuous bounded functions over R. This is exactly the same thing. This and this is the exact same correspondence, and a sequence of measures converges weakly if and only if the corresponding random variables converge in distribution. Okay. So this will be our definition of weak convergence. All of these are equivalent, but this will be our definition that we'll continue to use. Okay, that these convergence happens. Now we are ready to get back to random matrix theory, and let's go into the semicircle law. Okay, so let's say Mn is our random matrix with entries xij. This will be a Wigner matrices, and let's say lambda i's be the eigenvalues. Okay, but note that if I just sum over, actually the lambda i's are increasing to infinity, because if I sum over these lambda i's, the squares of the lambda i's, that is trace of mn squared, and that is trace of mn transpose, because this is a symmetric matrix, and so this is this. All right. Oh, by the way, one thing. Throughout the rest of the talk, I talked about real and complex Wigner matrices. For the rest of the talk, we'll just assume real Wigner matrices to make things simple. Otherwise, I have to put a star here and so on, and this will be a bar. This will be mod xi square. It's just extra notation. The proof is no harder or no easier. It's the same proof, but it's just a little bit of extra notation. We'll forego that. So henceforth, all Wigner matrices are real Wigner matrices, where the diagonal entries have some distribution, the off diagonal entries have some distribution. It's IID symmetric. Okay, and off diagonal entries must have mean 0 and variance 1. Okay, so yeah, where was I? Yes, if I look at this summation of lambda I squares, it's this, right? There are n squared terms in here. So if I look at the expectation is actually n squared. If I just, for the sake of argument, assume that the variance of the on diagonal terms is also 1. In particular, the lambda i's are typically of the size square root n. So they're growing. In particular, to make sure that like we have a sort of controlled process, we must look at lambda I divided by root n. We must look at this set, so that we can get something out of it. Okay, let's look at such a set and look at what happens. Let's say we sample a Wigner matrix Mn by sampling that entire sorry, sampling a huge uh, collection of random variables. We sample them. We look at the Wigner matrix Mn. We look at the corresponding uh, eigenvalues which are scaled by root n, and we plot them as part of a histogram. Okay, as you plot more and more eigenvalues, or rather, you should say as n goes to infinity, because yeah, then you get this sort of a curve. You eventually this converges to a semicircle type of law, right? So initially for small n it looked like this. As n grows to infinity, it eventually approaches a semicircle. The histogram approaches a semicircle, and the semicircle, of course, corresponds to a PDF. Oh, by the way, when I say histogram, I mean scale histogram, as in what proportion of points are in a particular uh, bar. Okay, instead of counting the number of eigenvalues landing there, I count the proportion of eigenvalues landing there. Okay, so that the total area under this curve is always 1. So if I look at such histograms, as n goes to infinity, I get this wonderful law, and this is called the semicircle law. I hope the picture is clear, but there are many technical snags going around. For example, Mn is a random matrix. These lambda I by root n's are random variables. All of them are distinct random variables. So the histogram that we obtain is random. This is one particular realization of the histogram. So what does it even mean for a sequence of random histograms to converge to a semicircle law? This requires, and this is where our previous discussions on measure theory come to help us. That is, how do we formalize this? And well, to do that, we set up a couple of definitions. Firstly, we look at the empirical spectral distribution. This is exactly what we had before. We look at this measure which assigns equal weights to all of these lambda i's by root n. Okay, so you have this lambda n over root n somewhere here and all of them, and it assigns equal weights to those, and this is that measure. However, note very interestingly that this is a random measure. All of these points are random. So the measure itself is random. And so you have this sequence of random measures, which basically represents this histogram. How? If you plug in this set, let's say this interval I, then mu n of I would give you the height of this histogram. Okay. We'll give the height. I don't know how to represent. Let's say h of I, height of this histogram. And if I look at this eventual law, this semicircle law, I mean, it turns out to be a semicircle uh, based at these 2 points. So the word semicircle is not exactly correct. It's a semi-ellipse. The height is somewhat less, but because the radius is 2, I mean, sorry, the radius is 2, but the height is not 2. So then the area would be larger. The height is 1 over, the height is 1 over pi. So it's a semi-ellipse, but it's still called the semicircle law. So this convergence of histograms can be interpreted as simply saying that mu n of I, if you fix any such interval I, mu n of I is the height here, which basically corresponds to the number of uh, or rather I should say, if you look at this interval, mu n of I is exactly the number of uh, lambda i's rescaled eigenvalues which are in this interval, right? That follows from here. So mu n of I, this is from this definition, it follows that this is number of i's such that lambda I upon root n belongs to this interval I. Okay, you have to divide by n, of course. And what this sort of convergence of histograms really shows or is expressing is that all of these intervals, mu n I, is converging to the semicircular law of I. This is precisely the area under the graph of the semicircle law for this interval I. So this convergence of histograms and all such things effectively expresses this fact. And as we have seen before, this fact is precisely equivalent to saying that integral f d mu n converges to integral f d mu for all f continuous or whatever, continuous bounded, let's say. And that is precisely the statement of that mu n converges weakly. Okay. However, as I was mentioning before, these are not just histograms, these are random histograms. So everything here, everything that's happening here is happening almost surely. And that is the statement of the semicircle law. By the way, the names, this measure which gives weight 1 to all of these random variables, weight 1 over n to all of these random variables, that's called the empirical spectral distribution. Okay, ESD. And sorry, and the limiting law, that's called the limiting spectral distribution. Okay, let me write the short form, LSD. All right, so yeah, let me state the semicircle law in its full glory. Is that, let's say Mn is a Wigner matrix, real or complex valued, both work. Then this empirical spectral distribution converges weakly to our semicircle law. Weak convergence is the only thing here because in the space of measures, that is the only natural convergence. And this entire thing happens almost surely. In other words, if unnecessary, let's not, if you don't want to deal with measures and all these things, what this is saying is that if you have any function, let's use some other color. if you have any continuous and bounded function, in fact, more is possible if you have any measurable function. But okay, if you have any continuous and bounded function, then summation I equals 1 to n of f of lambda is by root n. If you look at this average of this function, that is convergent to the integral of fx with respect to this distribution rho. Okay, so this is exactly integral f d mu n, because okay, look at this form of mu n and go back. If we go back, then this is precisely the integral with respect to such mu n's, such measures. So this is the correspondence here. This is equal to this, and this is the uh, integral with respect to the semicircle law. And again, f is a fixed function, but lambda is a random. So the left hand side is a random variable. So this convergence is also almost surely. Okay. So this is the statement of the semicircle law. Does anybody have any questions up to this point? I think this is a good place to take a 30-second break. And if there are any questions, please let me know right now. Now, from here on out, we'll hardly again be looking at measures. Okay, it's although no, we will be looking at measures, but we won't need any properties of measures at all. Okay, so if not, I'll go to the proof of the semicircle law. This semicircle law was okay. A little bit about the history, maybe. This was proven in 1956 by Wigner. He came up with those matrices, and this was his first key result, and this is the result that sort of started off random matrix theory. But let's take a second to ponder this. The limiting distribution has absolutely nothing to do with the with the precise distributions of the entries of the matrix. It has nothing to do with xi or xid. This is indeed a universality result, and this goes to show that if we go back to, let's say, Wigner's original idea, what he wanted to do was understand this Hamiltonian, right? The eigenvalues of the Hamiltonian, the semicircle law, and there are other laws, other universality laws, which basically show that there is no need to look at the best approximations or something. Whatever random matrix you choose, whatever classes of random matrices you choose, the point process of energies has the same structure. It converges to the same thing as long as you take care of the scaling by fixing the variance. So it doesn't really matter how you approximate it, you will always get the same result. And indeed, H hat turns out to have the properties very similar to such like these matrices, and that's why what Wigner tried to do was successful because of a statement like semicircle law. Okay. All right. Then let's yeah. Then let's proceed with the proof of the semicircle law. And if you look at the law, I mean, if you look at this, what does it say? This is 1 over n summation delta lambda I over square root n into n. This exactly looks like the strong law. Convergence almost surely. A partial averages converging almost surely. So yeah, and the proof will also be sort of analogous to the semicircle law, to the strong law of large numbers. Okay, so the strong law is this exactly, right? You have to have an IID sequence of random variables. Let's say the variance is bounded. That's not necessary, I think, but it's still there. Then our this is a good estimator of the mean, right? That's what the law is. That this converges almost surely. That these empirical means converge almost surely. And let's go back for a second and look at how we proved it. I actually wanted to give this talk last semester because last semester Arthadeep gave I think a proof of semicircular law. So I could just refer to that. Even now I'll be just referring to that. But the first step almost always is truncation, is that proving that uh, proving the semicircle law for bounded random variables would be sufficient. So there's a natural way of going from bounded random variables to general random variables. The second statement is actually this, showing that xn hat minus expectation of xn hat goes to 0 almost surely. And there is also a third statement, which we don't really prove in the semicircle, in the strong law, which because it's obvious that the expectations converge to the mean. I mean, the expectations are equal to the mean, so there's nothing to prove here. But there will be something to prove in the case of semicircle law. Okay. But before we actually start talking about this sort of idea proof in a semicircle law, our xn hat will be replaced by 1 over n summation delta lambda I upon square root n, right, which is mu n. So in order to carry over this sort of an argument, we need a definition of an expectation of a random measure. And that's very easy to give, in the sense that you can just say that measure of a set, the expectation of the measure of the set A would just be the expectation of the measure of the set A, because it's a random measure, right? There are, oh, I've written it down already. So for any random measure mu, this will be a deterministic measure which has this property, and consequently, for any function f, if you integrate with respect to this expectation measure, that would be the same as showing that that would be the same as integrating it first and then taking expectations. Okay. Let's discuss a quick proof outline for the semicircle law. I just stated the law again here. And here it's very same. It's very similar to what we saw in the case of strong law. We first do a reduction. And the reduction is that it suffices to prove the semicircle law under these conditions. Well, this was sort of our assumption, so there's no need to put it back again. But it's enough to prove for bounded xi and for zero diagonals. Okay. So now these xi's look like this somewhat. X11 is 0. You have x12, x13, and so on. This entire diagonal is 0. And all of these have been replaced by bounded random variables. Okay. And this first step shows that it is sufficient to prove for such cases. There is no need to prove the general case, or rather, there is a way from going from the special to the general case. And once we have this sort of a boundedness, we can go back to our standard thing that mu n minus expectation of mu n goes to 0 almost surely, and showing that expectation mu n, this expectation measure, these are deterministic measures, this is converging weakly to the semicircle law. There's no almost surely here, both sides are deterministic. This is probabilistic. Okay. And what we will do in the today's talk is this was the approach taken by Wigner as well. And this is this is always the standard approach. But what I'll do is I'll mainly focus on this part. And this is the crux of the proof. Okay. So both of these are mainly like almost like analysis. You don't actually see any probability here. Here you do see probability, but just one application of Borel-Cantelli lemma, and it's done. And this is purely analysis. So I'll focus mainly on 3. 2 and 1, those are technical proofs. I'll ignore them. Okay. But 3 also requires some work. That's what I wanted to say. So I hope the goal is clear. If there are any questions, let me know while I drink some water. Is converging weakly to another measure. How do we show that? Well, there's a nice way of doing it called the moment method. Okay. So let's say we define the moments of a measure in this way by the expectation of x power k. And we are all familiar with moments of random variables, and we know that they carry a lot of information about the random variable. However, they might not characterize the random variable completely. In particular, there are these two densities which have the same moments, but the densities are different. Okay. However, one can talk about a particular criterion called the Rees criterion, which says that if the moments are well controlled, if the moments don't grow too fast, this m2k is the 2kth moment, then the random variable is completely characterized by the moments. Okay, and in the abstract, I just said that we'll assume some black boxes. This is one of the black boxes we'll assume. In particular, if we are interested in showing convergence to the semicircle law. So if you take the semicircular density and you compute the moments, you will see that these are precisely the kth Catalan numbers, which is a funny coincidence. And not exactly a coincidence, but a funny result. And the k plus 1 moments are 0 because it's an odd function. So in particular, if you just do this expression, you would see that this is goes to 0 as k goes to infinity. So the supremum is finite. In particular, this satisfies the Rees condition. So if we can just show that the moments of a given random variable are this, that random variable must be the semicircle law. Okay. And we also have a wonderful method for proving this weak convergence called the method of moments. Most of you are familiar with it. Is that if you have a sequence of measures converging to another measure, that is and like let's say you have a measure nu which is characterized by its moments, then these two notions are equivalent. That whether nu n converges to nu weakly is the same as saying that the moments converge. Okay, this is like true for probability measures. For arbitrary measures, some things can go wrong, but this is the method of moments, and this is what we'll employ to prove our step 3. Okay, so let's say nu n is equal to expectation of mu n, and then the kth moment, if we wish to compute it, we can take this expectation out by definition, and if we compute this expectation, we get this basically, right? It's 1 over n expectation of sums of kth power of those normalized eigenvalues. In particular, if I take this n to the k over 2 outside, this is exactly the expected trace of mn to the power k. And this is called the trace formula. And I won't say much more about this, but this is sort of the basis. But okay, if we wait here for 1 second, let's say you define a linear functional tau, which is like 1 over n expectation of trace of something. Okay, so this formula just says that if I just define a linear function like this, then this formula reads mk of nu n equal to tau of mn power k. This almost looks like the moment of this. It almost looks like the moments of this random variables are the moments of these matrices. So we can almost give a distribution to the matrices. Like we can almost, this is almost analogous to saying that nu n is a distribution of mn in some very vague sense. And this formula is the starting point of a wonderful theory called free probability. I should not say starting point, but rather the motivating example for something called free probability. But just wanted to point it out. Yeah. So in particular, if you say, let's say mn is xij as we have been using, then this is precisely expectation of this sort of a this product. Okay, xij's I1, I2, I2, I3, and finally ik to I1. And note, remember one thing, that we have assumed the diagonals to be 0, right, by our reduction. So I1 not equal to I2, I2 not equal to I3, and so on. It's not that these are distinct, but the adjacent ones are not the same. This is something we can assume, right? So now let's actually, this is an expression for the moments. let's compute some moments. If you look at the first moment, this sum is basically an empty sum because I1 is not equal to I2. So like it has to be expectation xi1 xi1, but no such term exists. So this is an empty sum. So the sum is 0. And that's good. We want the first moment to converge to 0. Remember what were the moments of semicircle law? They were precisely the Catalan numbers in the case, in the even cases and 0 in the odd cases, right? So this is good. What about the second moment? This would be fun. If you look at this, it will be 1 over n squared summation ij expectation xi xj, and xi xji is the same as xij. So this just becomes this. So you get n into n minus 1 by n squared. There are n into n minus 1 many choices for I and j such that I is not equal to j. So you get 1. In the limit, it's going to 1. And that is indeed the first Catalan number. So we are happy. What about M3? M3, if there are multiple things that can happen, let's say. So basically, what are we trying to do? Just a second. Yeah, in M3, what we are trying to do is we are looking at things like xi1, I2, xi2, I3, and xi3, I1, right? This sort of expectations. But whatever choice you make for I1, I2, and I3, one of the three would be 0 that you can check. Like one of them will be x LL, something like this, and they'll be 0 because, yeah. So this is again some sort of an empty sum. But let's, instead of saying, okay, I'll do one thing. Instead of imposing these, okay, okay, we'll keep these conditions imposed. It's not an empty sum. However, what can happen is, let's say you can have these two conditions. You start from I, so I1 equal to I2 equal to j, which is different from I, and I3 must be I, right? But in that case, you have this, like you run into various issues. So you can just check that this sum is 0. However, we need some sort of a way of computing nth moments or kth moments. How do we do that? Let's do a little bit of a graphical representation. This product x I1, I2, I2, I3, and so on, let's represent it by x I tilde, where I tilde is just this vector. Okay, where I alphas, these are taking values 1, 2, all the way up to n. Remember, because we are dealing with the n cross n matrix. So yeah, so that can be expressed as a graph like this. You start from I1, go to I2, go to I3, go to I4, and so on. Go to In, then you come back to I1. For example, let's look at this graph. I to j, j to I. So this graph looks like this, right? You have I, from there you go to j, from j you come back to I. Yeah. Similarly, this graph is from I, you go to j, from j you go to I, from I you stay at I. And what we have, by our definition, the moment a random variable has self loops, it's gone because xii is 0, right? So the only graphs in which you can you have three edges and you start from a vertex and you have to come back to the vertex, it has a loop regardless. So it can be like this also, x I to j, j to k, k to I. But here the problem is, here, oh no, k but l. Okay, so what happens here? The problem is all of these edges like xij, xjl, xli, these are all independent, mind you. So what happens is that this splits up xij, xjl, expectation xli, and expectation of any random variable, any of this xij's is 0. So this term also does not contribute. Okay, so either you get a loop in the third moment case where the term is automatically 0, or you get unpaired edges. If you have edges like this which are paired up, then those terms come together to give square and it doesn't become 0 automatically. However, if your graph has an unpaired edge, the corresponding term is 0. Okay, So we can note this as an observation that if gamma I has unmatched edges, then expectation of xi is 0, because this xi tilde will have a term, an isolated term, which will not be squared or cubed, and by independence that would just come out and the expectation of that would be 0. Okay. All right. So let's compute the fourth moment. Well, how does one compute the fourth moment? What do we need? We need something like this, right? We need some sort of a. So instead of, like previously we were summing over this, and we saw that summing over these sort of sequences was the same thing as saying that summing over xi tilde. All right. So, but what form can this graph take? The graph can be like this. Like we start from I1, go to I2, from I2 to I3, I3 to I2, I2 to I1. We have to go to I3 and come back. So we have to start from I1, come back to I1, right? That is like the last term is I and I1. So we have to come back to I1. And there are n terms. Sorry, there are k terms here. Oh, so this should be ik. I'm sorry. Yeah, that's a mistake. Oh, wait. Anyway, so, and if you look at terms of this form, you get x I1 I2 squared x I2 I3 squared, because this edge I1 I2 has come once and twice, I2 I3 has come once and twice. So you get these terms. And by the way, you get this 1 over n cubed because here you had this expression, you had the scaling, right? So you can have these kinds of graphs where there are no, we saw this observation says that whenever you have an unmatched edge in a graph, so you have some graph which looks like this. So you go there, come back, go somewhere else, and then come back, let's say. This are all unmatched edges. So that will correspond to 0. So those terms don't contribute. So the only terms that do contribute are these three kinds. You can check that easily. And then the problem is, and to see how much these contribute. Well, look at this case. X I1 I2 squared, x I2 I3 squared, these are independent. And the variances are 1. So this term is equal to 1. This term is also equal to 1. This term is not 1, but it's bounded by some, I don't know, some c power 4, right? Because the random variable itself is bounded by c power 4. So this term that we have, the extra term, this is bounded by this, and this goes to 0. However, these two terms don't go to 0. There are three choices, I1, I2, I3. So there's n into n minus 1 into n minus 2 ways of doing that. So that converges to 2. Like this converges to 1, this to 1. And that is indeed our second Catalan number. So now the question is, how do we do this in a more systematic manner? Let me look at the time once. Oh, it's already very late. Yeah. So let's, in the general case, I'll go rather fast. The reason being that this is basically unnecessary technicalities almost, but it's quite combinatorial. So we are looking at graphs which have like this sort of path graphs which have k edges, right? So in the computation of the kth moment, we're looking at the graphs with k edges. So we divide them into a few parts. First one, let's say C1k. These are graphs with one lone edge. Just one edge where there is no edge going back or another edge going front, nothing is there. So these are just graphs with lone edges, right? And the moment you have a lone edge, that term doesn't contribute. So such graphs have no contribution. Secondly, if you look at unlabeled graphs where the edges are all paired up and the underlying graph of paired up edges forms a tree, something like this. So this forms this sort of a tree and every edge is paired up and so on and so forth. That would correspond precisely to the terms that we had here. Both of these are graphs which are paired up completely and the underlying graph forms a tree, right? So there, if you do the computation, it will be exactly the same. It will be some x e1, x ek by 2, whatever. All of these are 1, so that's not a problem. And there are k by 2 plus 1 many choices. So note that there are k plus the number of vertices. If you have a graph on k edges, the number of vertices would be 1 plus k over 2. Okay. So if you have that, you're looking at the summation. The product inside is just 1, and the summation is from I1 to ik over k by 2 plus 1, and that precisely is sufficient to counteract this n to the power 1 plus k over 2, and so it goes to 1. All right. And the third case is graphs like this. If we go back to this case, this had way too many edges and way few, like this is the number of vertices was too less. If you have to counterbalance this term 1 by n to the 1 plus k over 2, the graph should have enough vertices so that there are enough choices so you can counteract. In the third case, the number of vertices was way too small. So as you can see that the number of vertices is strictly smaller than 1 plus k over 2. So this goes to 0. Whatever contribution this has, each of those graphs, that goes to 0. So yeah, I guess I didn't lose the thread, but went a little bit carelessly through this. So basically what we did was we had this summation, we divided it up into 3 parts. One part was 0, exactly 0. These are those indices where the corresponding graphs have lone edges. So that's exactly 0. The second part was which had the only non-trivial contribution. That was the graphs which were like this, right? So every edge was paired up, and the graph of paired up edges formed a tree. And the rest of the things, the number of vertices was too less, so they did not contribute in the limit. All right, they had a non-trivial contribution, but they did not contribute at the limit. So finally, what we get is, if you look at this moment from that formula, you get a little o of 1 terms. These will go to 0 as you take n goes to infinity. And the only contributing terms are the number of CK2s, the number of graphs which looked like this, which the edges were all paired up, and the paired up edges formed a tree. And this is a fact from combinatorics that if you have uh, a graph on k edges such that all the edges are paired up and they form a tree, the number of such possibilities is this. It's precisely k choose k over 2, 1 over k over 2 plus 1 if k is even, or 0 if k is odd. And that's where you see that the fact that the semicircle law has the Catalan numbers as its moments is very, very significant. And this actually completes our proof. So we have shown that all the moments converge to these Catalan numbers, and hence the distribution must converge to the semicircle law. Okay. The step 2, I don't really want to talk about step 2 or step 1 because those are standard analysis things. You use Borel-Cantelli lemma, you use some tricks from real analysis, linear algebra, and that would be done. Okay. So yeah, that there is the proof of the semicircle law. But let me talk for about one unsettling point here is that this all of it seemed like magic. We said that okay, this our sequence of moments converges to this sequence of moments. The semicircular law has precisely the Catalan numbers as moments, so we are done. But how did we did not derive the semicircular law at any point. We just said okay, semicircular law has the same moments, so we have a proof that it converges. But how did we get the proof to begin with? How did we guess the semicircle law? One can say okay, you look at the histogram, you guess it. But that's not true in general, right? Like it's very hard to do that. So can we do better? Well, let's go back to the proof of Fourier, like the Fourier analysis proof of the central limit theorem, right? So what do we do in the central limit theorem? We say that okay, the distributions converge if and only the Fourier transforms converge, that is the characteristic functions converge. And then from getting the distribution from the characteristic function is not too hard. There's a way of doing inverse Fourier transform, right? However, if we employ the same technique here, we can define a Fourier transform for these mu n's, and they would look like this. They would come in terms of these matrix exponentials. However, there is a fundamental problem that the main property of exponentials is no longer there. The exponentials, like the product of exponentials, is no longer the sum all the time because x and y are non-commutative things. These are matrices. So this happens only if they commute. And so that's a problem. Fourier transform is not much of a help here. There are ways to generalize the Fourier transform using something called Harish-Chandra formula, which actually does give us another proof of the semicircle law, but those are way too complicated and like an overkill. However, our idea that we have to use some sort of integral transform is actually correct. So let's try that. I'll just give an overview of this Still-Just transform method. This is another integral transform, just like Fourier transform, Laplace transform. This is another transform. Whenever you have a measure mu, we can define the corresponding Still-Just transform of that measure. Okay, and this is a complex valued function. This is a function on the complex plane. It takes in complex values, gives out complex values. Indeed, you can show that uh, it has a conjugate invariance, and it takes the upper half plane to the upper half plane. Such functions are called Hergold's functions, and they have very nice properties, which we won't discuss here. Further, this function is also holomorphic on the upper half plane, and in particular, you have it's a complex analytic. It has an expansion. Holomorphic just means complex differentiable, by the way. So it is complex analytic. It has a power series expansion, etc. There are also nice decay properties of this. I just listed the properties here. You don't need to really look at it. But the main thing is when we prove the central limit theorem, we do two things, right? We first say measures converge if and only if characteristic functions converge. And secondly, from the characteristic function, we need to recover the final measure, right? So those two things are exactly there here as well. So we have this continuity theorem is that if mu n be a sequence of random probability measures on R and mu be a deterministic measure, then mu n converges to mu if and only if the Still-Just transforms correspond, like converge, and in the appropriate sense, almost surely, then this gets almost surely. If this convergence is in probability, then the convergence of Still-Just transforms is also in probability. Indeed, the same is true for the expected measures. Okay, the expectation mu n converges to expectation mu if and only if the expected Still-Just transform converges to this. Mu is deterministic. So expectation of this is a complex value thing. Okay, that's the continuity theorem. And you also have this inversion formula. Inversion formula is if you have the Still-Just transform, there is a way to recover the original measure, the original density. You can recover the rho x. So this basically has all the things that we need. The only question is it good to handle? The reason we ditch the Fourier transform or the characteristic function is because this function is quite a bad behaved function. It's like x plus y, those commutation things are not there anymore. However, as it turns out, this Still-Just transform is very, very well adapted to working on to our proof of semicircle law. I'll just give a quick outline of the proof. I won't go into the proof at all. If what do we want to show? This empirical spectral density converges to our empirical spectral density converges to the semicircle law. Instead of showing that, let's say Sn is sorry, Sn is our Still-Just transform of this mu n measure. Then there are these three steps that we can show that Sn and Sn minus 1 are sort of comparable. The gap is small. Expectation Sn can be sort of recursively. Oh, there's a mistake here. Sorry, this should be Sn minus 1. There is a way of recursively getting the expectation, like a recursive relation between the corresponding terms of expectation Sn. And thirdly, that expectation Sn actually does converge to some S. But once we have shown these things, This limiting Stieltjes transform must satisfy something like this because of point 2 and point 3 together. In particular, we can solve this. We can get Sz is minus z plus minus root over z square minus 4 by 2. But notice what I said in the beginning. It's a Hergold's function. So it must take the upper half plane to the upper half plane. In particular, this must be a plus. So we are basically done. Indeed, if you know what the generating function of the Catalan numbers is, bells should be ringing in your mind. This is the generating function for the Catalan numbers. And if you want to really wish to find the limiting density, you do the subtraction, divide by 2 pi I. By the way, this is precisely uh, 1 over pi times the imaginary part of Stieltjes transform. Okay, this sort of an expression is just 1 over pi times the imaginary part because S of z bar was S of z whole bar. And if you do that, you get an expression for the Stieltjes transform. Okay? Yeah. So this is a way in which you can actually extract the sorry, you get an expression for rho x for our semicircle density. This is a way in which you can extract the semicircle density out of it. There are many proofs of semicircular law. Semicircular law is one of the most proven things in like probability or random matrix theory. There are at least 5 or 6 proofs. There's a proof using free probability. There is a proof using other weird techniques on Nolan-Beck processes and so on. But these are the two most basic proofs. I wanted to just give an outline. But now it's time to talk about some like variants of semicircle laws. And this will be quick. I won't go into much detail here at all. So let's talk about some other results. Firstly, what we did was we looked at our eigenvalue distributions, like this is say minus 2 to 2, and we looked at some interval in between and said, okay, what is the how does the point process of eigenvalues on this interval look like? Answer was mu and I is eventually converging to rho of I, right? However, what if there are around n eigenvalues, like of the order of n eigenvalues here, because the typical gap is of the order of 1 over n. So can we say something more precise about fewer number of eigenvalues? That would require us to shrink the gap. Shrink the gap I, like make it in instead of I, and shrink it. And yes, we can. As it turns out, using the techniques that I said in the second proof, the Stieltjes transform method, that's a lot more suited to really understanding the fine structure of this point process. And we can show that as long as the size of such an IN is it's like more than 1 over n, n should be small, more than 1 over n. So typically around n to the epsilon eigenvalues are contained in this I. Then with very high probability, these two converge. Like these two are a little off one. So one converges to the other. I mean, converges to the other is not a correct statement because both of them converge to 0. But yeah, so the gap between them is small. Okay, so we have a semicircle law for smaller scales as well. And these Green's function techniques also lend themselves very beautifully in proofs of other results involving eigenvalues. For example, we have something called the eigenvalue rigidity. Okay, so if you look at Green, yes, if you look at this interval from minus 2 to 2, let's say the ith eigenvalue, where is it supposed to be placed? Typically, where do you expect it to be? Well, it should be in the I by nth quantile of rho, right? It should be somewhere here. Let's say gamma I is the I by nth quantile, so that satisfies integral from minus infinity to gamma I of rho is like I over n. Right? So this is the typical position of the eigenvalues, and what this says is, well, it doesn't deviate much from it. Lambda I by root n minus gamma I, this is basically of the order of 1 over n, as long as it's far enough from both endpoints. Okay, and all of this happens with very high probability. And also, if you look at one question we never asked or answered, is we just talked about eigenvalues. What about eigenvectors? As it turns out, the eigenvectors are delocalized. Like, you never get something like 1 0 0 0 0 0 as an eigenvector. All of the coordinates will be of size 1 over square root 10. Okay, all of the coordinates will be of size 1 over square root 10. Squaring that will be n. And this term delocalization and all, maybe I should explain it like in one line. The eigenvectors, let's go back to our Schrodinger equation, H psi equal to E psi. The eigenvectors of that equation correspond to actual physical states. Okay, so they are physical states where with energy EI. Okay, if that is the corresponding eigenvalue. This just shows that those states, all of those states, will be delocalized. That is, if there are multiple sort of, I should say, multiple places in which energy can be distributed or a particle may be distributed, then all of them, then the particle is indeed distributed. It's indeed delocalized uh, among those states. Okay, so all of them typically have 1 over square root n. Yeah. Um, Maybe I wanted to give a brief idea about how to prove these results. Maybe just this particular result, semicircle on small scales. The idea is that basically what did we do to prove our global semicircle law? We said that SNZ minus S, the still just transforms. This gap is like 1 over n. Okay. However, if you write out Z completely, this O of 1 over n is not exactly correct. So this should actually be, if Z is E plus I eta, it should be 1 over n eta. This is the standard way of writing Z. And then you can show if you write it in this form and you take eta to be n power epsilon over n to be decaying fast. So you're looking at regions here, like approaching this line, the real line, from the upper half plane. If you do that, then you would have that SNZ minus S rho Z, this gap between the Stieltjes transforms, that's still decreasing. And it requires a little bit of proof, but and this would actually imply the first result, that a local. So this is why the Stieltjes transform method is nice, is that local control on the Stieltjes transform corresponds to local control on eigenvalues, or I should say local control in that, in the sense that, okay, so controlling the Stieltjes transform for small eta. Eta is the imaginary part. This corresponds to local control on eigenvalues. And the reason is that if you look at the imaginary part of this Sn, if you look at the expansion, you get a quantity like this. And this expression looks like this, right? So beyond an interval of eta, it decays off very fast. And within an interval of eta, it's somewhat large. So there's a sharp transition here. So if I look at this function, this summation is effectively counting. So basically each function sort of looks like this indicator that lambda root n minus e is smaller than lambda. That this e that you're using will catch only those lambda I by root n's which are within an epsilon distance of within an eta distance. So yeah, this is it's not an explanation really, but it's a heuristic to say that okay, this is why you can use Stieltjes transforms to get local control. There are other results. For example, whenever you have, so semicircle law is sort of an analog of the law of large numbers, right? Then whenever you have a law of large numbers, the next question is what is the central limit theorem? What about the fluctuations? Can we say something about the fluctuations? Here also the answer is yes. we can say a lot about the fluctuations, and that's a very, very interesting topic, which has quite a long, like a 30-year history. It's a very, very dense topic. So in the semicircle, in the central limit theorem, we know that if we scale by square root n, the gap that goes to normal 0, 1. Here, however, as it turns out, you have to scale by n to go to normal, and it has a very similar behavior, but you have to scale by n. And the reason is, in the central limit theorem, there's a lot of independence. These summation xi's are quite free. Xi's are completely independent. These partial sums are somewhat independent. However, these eigenvalues are highly correlated. So this convergence happens a lot faster. In particular, to get something non-trivial, you have to multiply it by a larger number so that it converges to a non-trivial random variable. So the fact that this is square root n and this is n tells us basically that the point process here is highly correlated, but the point process here is not. Okay, and there's an expression for this variance. However, so there's this funny thing that if you're looking at smooth functions, you would get this sort of a convergence. However, if you're looking at functions which are not smooth, I think the smooth can be reduced to something like C2, but not beyond that. In particular, if you're looking at functions which are not smooth, then you get other kinds of behavior. Instead of scaling by n, you have to scale by n by square root log n, basically, so that it goes to something non-trivial. Okay, and that has to do with the fact that this integral will not exist, and so on and so forth. All right, and the like a full, complete analysis of all the fluctuations is very, very complicated. It requires quite a bit of work. And finally, the last thing I wanted to talk about is this question: what if the matrices we're dealing with are not Hermitian? Throughout this talk, we have only been dealing with Wigner matrices. What about, say, IID matrices, where each entry is, say, independent normal 0, 1? What about such matrices? What happens then? Here, however, like previously, all our eigenvalues were real. Now they're no longer real. They're complex. And as it turns out, just like before, we had eigenvalues distributing on the real line in a semicircular distribution. That was just a distribution, but they distributed on the real line. Here, the limiting here again, it has a limiting distribution, and the limiting distribution is uniform on the unit disk. On this is, by the way, in the complex plane. This is just mod z less than or equal to 1. On this set, the eigenvalues eventually distribute out uniformly. And okay, you can notice one thing. In this case, it's the matrices had real entries. Here they had complex entries. So here the eigenvalues are symmetric about the upper and lower halves, but in general they're not. In the complex case, no such structure exists. And analysis here is much, much more difficult. I cannot emphasize how much more difficult the analysis of this non-Hermitian matrices are, because the spectrum, previously you had a Selges transform and you could talk like the spectrum was very stable. This is, of course, this is, I mean, I'm pretty sure this what I'm saying is very vague, but here the spectrum is very unstable. Anybody who has worked with non-Hermitian operators will tell you spectrum behaves in a very, very bad manner. However, we still have this circular law. This was conjectured way back when, and the circular law is precisely that: the spectral density is converging to the uniform distribution almost purely and in probability. Okay, so and all of them are IID xi with mean 0, variance 1. Okay, and I mean this has such a long history, this law. Like in 65, it was first proven by Mehta for complex normal entries, which was later on done by adapted by Edelman in 1988, which was much, much more tricky. And like after a long battle of what is it? It's almost like 50. It's more than 50 years, right? No, it's almost 50 years. Finally, this was proven by Tao and Wu in 2009. And one main input which I wanted to include, that's why I said it, is Gurko in 1984. So like previously you see that mostly they were doing it for specific distributions. Gurko was the first one to give a approach for the general case, and he gave a quote unquote proof. But the problem was his approach was quite non-rigorous, and he was using bounds which were not even proven to be true. He was using bounds on singular values of these matrices which were not known. However, his approach was fruitful. It was key to the argument by Tao and Wu. And by the way, this is there's no gap here. I just didn't write things. Every year there was some paper or the other. It was like 30 years of intense work which led up to Tao and Wu's complete general case. So I'll just give like brief tools of the proof. There's something called Gurko's hermitization technique. It's a way of taking these non-Hermitian matrices and embedding them inside some other Hermitian matrices and concluding spectral properties of the non-Hermitian one using the properties of the Hermitian one, which were well studied and well known. This involved two things: bounds on something called the logarithmic potential of these matrices and bounds on the smallest singular value. And in the something like 2000, in the 2000s, this was a very active field, 2000 to 2010. It's still an active field actually. And it was largely due to the fact that people could get some sharp bounds on the smallest singular value that Tau and Wu could prove this general case. In particular, actually, like if I should mention, like in 2007, I believe, Tau and Wu gave bounds to the smallest singular value, and which were later improved in 2008 by Rudelson and Verschinen, which effectively formed somewhat the basis of this proof. Okay, this was the last bottleneck in Gurko's approach, which had to be removed, and that was finally removed in 2009. Okay, yeah. Well, that's the end of my talk. Thank you so much for attending. I think I finished on time. Yes, I did, but well, I it was a little bit rushed. So, are there any questions about the talk? So, let me quickly summarize what we did. We looked at the semicircle law for random matrices, which talks about this point process of eigenvalues and what is the like overall convergence, like what does it converge to, that point process. Secondly, we looked at two proofs of this. First one was mostly a combinatorial proof, which was originally due to Wigner, which uses basic techniques, but it's not very generalizable. Secondly, we looked at using a technique using the Stieltjes transform, which is a very generalizable method, and it generalizes to some other uh, variants of the semicircle law, the local semicircle law, and some of its applications. Finally, we looked at fluctuations of the semicircle law because it's a limit law, and well, whenever you have a limit law, you need to look at its fluctuations, but it's a very interesting and complicated story. And finally, we looked at the circular law, which is sort of like the semicircular law, but for non-Hermitian matrices. Okay. And the fact that the circular, like this was one of my questions is, can you somehow start from the circular law and get to the semicircular law? Because it feels like too much of a coincidence. In fact, there is something else called the quarter circular law, which is also true for um, some sample covariance matrices. So as it turns out, there is a way of starting from the circular law and going to the others, but that approach involves tools from free probability. So sadly, I could not discuss this, and I also could not discuss this because I'm not insane. Doing it in one day, it's completely insane. Okay. So any questions? If not, here are some references to these topics. The first two are books by Tao and by and Silverstein. These contain basically both of the proofs of semicircular law presented in complete detail. And for like the history of the semicircle of the circular law and a proof of the circular law, you can look at this wonderful article by Bodhanavi and Shafai called Around the Circular Law. All right. If not, maybe I'll stop sharing the screen. I am audible, right? uh,
Yeah.
yeah, okay. All right. So, all right then. Thank you so much. We'll let you know about further math club talks down the line. And I would request you guys to also come forward, give your talks, tell us what topics you're interested in, so that we can find speakers to talk on those topics. Random matrix theory was sort of a highly requested topic, so that's why I wanted to talk about it. But we would like to know what you guys are interested in. So I would request you guys to please uh, present talks, come up with talk ideas. Yeah. And if you, and like, we don't want to do it, but if there are enough people requesting foundational courses on topics which are like being covered in their courses and they are facing problems, we can organize those as well. But yeah. Okay.
Uh, Shashwat, a quick question.
Yeah, yeah.
Any update on correlated entries of matrices?
Yes, yes, yes. So this is a, okay, that's great. So let me go there. uh, all of this, so there is this class of matrices called generalized Wigner matrices. Okay. So they look like this. They are uh, Mn, which is some Xij n cross n. Uh, you assume mean 0, expectation Mn is 0, but you don't assume that the variance is 0. Okay, so all of these entries are correlated in some way. In particular, you look at this variance tensor S of R. This is equal to expectation of R Mn R, I think. Yeah. So if you look at this variance tensor, and the moment you know that it's mean, by the way, mean 0 can also be, I think, dealt with, but let's just like a mean profile can also be there. But if you have this sort of a covariance structure, if from here you can find the covariance structure, it still, the semicircle law type result still holds, but the limiting distribution is no longer the semicircular law. It is something else. Okay. In fact, let me take you back here. Where were we? Yeah. In the outline of this proof using Stills' transform, how did we get the semicircle law? We eventually got this sort of an equality, and from here we derived the semicircle law, right? In general, there is something called the matrix Dyson equation. So if in such a setting, there is something called the matrix Dyson equation. I sadly don't remember the equation off the top of my head, but what it does is it gives you the limiting distribution. It gives you the limiting distribution in this case. Okay. And that limiting distribution is completely determined by this variance correlation tensor S. Okay. So semicircle law type results holds and everything holds. So this framework, I mean, of course, Wigner started it in 1965. Hopefully, we have made some progress, and we have made very good progress. So this framework of Wigner matrices has been extended far and wide to include many, many kinds of matrices. And yeah, so you still get a result like semicircle law. I think the fluctuations are still an open problem. I don't think it has been done. The fluctuations are open, but proving circular law, that is much harder. I don't think for correlated entries you have a circular law. There are cases where one expects a circular law, but we don't know. For example, when you're dealing with sparse matrices, this is not correlated, but still let's talk about it. If you're dealing with sparse random matrices where each entry is IID but multiplied with another IID Bernoulli P, even in those cases you have a sparse circular law. And often whether you can get a circular law or not depends on number 2 and number 3. Number 2 is mostly, I believe it's not too hard in general, but number 3 is harder, like getting bounds on the smallest singular value. And the moment you get a bound on the smallest singular value, you can try and prove the circular law for such matrix ensembles. However, IIDness is, I think, sort of important in all cases. It's very hard to get rid of that. But for Wigner matrices, you can get rid of that condition. Okay.
Yeah, thanks.
Yeah. Are there any other questions? Okay. If not, I think thank you so much for attending. Yeah.